Thank you. Everybody hear me okay? Good? Okay, so this is a talk on resilient architectures, which is something that I've spent a decent amount of my time over the last 2 or 3 years trying to understand and then help, as he mentioned, enterprise IT bring these ideas into that space, which is where I spend all of my time. My name's Matt. I work at Pivotal Software as the Global CTO of Architecture, which is a really fancy title for I spend a lot of time with people helping them to understand what is architecture and how to employ modern architectures, cloud-native architectures, whatever name you want to pick for that, effectively in banks and retail companies, insurance companies, and on. So I want to start with some anonymized recent technology headlines. And you may have experienced one or more of these. In a room this size, you may have been a part of one or more of these. It's possible. I'm not here to shame anybody, but to draw attention to the problems that we're trying to solve. If you think about retail companies, they make most of their money in a very small segment of the year. And if they have a spectacular software failure during that time, whether it's online shopping or managing the sale inside of a big box retail store, if they have that failure and they can't capture that revenue at that point in time, they usually don't have another opportunity until the same time a year later to actually make that up. And so it can be very problematic for that business to not receive that cash flow. This one's near and dear to my heart due to my pathological lifestyle of spending a lot of time on planes. When the software fails, and about 3 or 4 times in the last 2 years, we've seen a significant failure of airline software that has stranded passengers for several hours, in some cases even stretching into 1 or 2 days. And if you think about the stress that that places on the airline systems, passengers are not where they need to be, but the planes are already filled, so we usually can't just take all of those passengers and shift them to the next flights. Not only that, those planes that should have flown from A to B are not at B, so they can't pick up the schedule that they had to go from B to C, and we have the same thing with flight crews. And so the entire system, for maybe a 2-hour failure of software, can actually throw that airline off for as many as 2 or 3 weeks in terms of trying to recover back to a base level of performance. And during that time, they lose also a lot of money. We can build software that meets all of the functional requirements. All the user stories were happily accepted. And yet, when everybody shows up to use it, the software crashes, the servers melt, and no one can use this beautifully designed thing. I was one of the people who used to stay up until 3 a.m. when they would launch the next version of the iPhone in the store, and usually within 5 minutes, by 3:05, you couldn't actually purchase anything more because the store would be down. You would go to your carrier, same effect. And you kind of wonder, 5 releases in to this device, why have we not managed to correct this problem? More recently, we have, it seems every 2 weeks, we have 3 or 4 huge security breaches in software that lead to the loss of personal information, financial information, and this leads to identity theft, this leads to loss of trust, ultimately, again, a lot of dollars, and a lot of people's lifestyles affected by this. You know, growing up, computers were around, and they were part of how business was transacted, but a computer failure didn't exactly change anyone's life at that point in time. But we're now reaching the point as we put more and more of our businesses, more and more of our trust, more and more of our livelihoods into software. These software failures can have very huge effects on real people, our friends, our families. And so we need to figure out how can we approach this in a better way. You know, we talk about disruptive companies moving very fast. Facebook made the statement, move fast and break things. And all of us that spend a lot of time working in heavily regulated companies said, yeah, we can't do that. That'll never happen. We have to figure out how can we move fast and not break things. Well, as it turns out, a lot of these companies have figured out the way to achieve that exercise. They approach resiliency quite differently than how enterprise IT has done it as long as I've been doing this. I've been around for about 17, 18 years, and our major process has been mistake prevention. Let's figure out how we can apply just more testing, more approvals, more release management, more phase gates, more sign-offs, more code review, and if we do enough of that, we'll somehow figure out how to write perfect software. We won't make any mistakes. And of course, we figured out that that doesn't work. Not only does it not work, when we make those mistakes, we have this massive process in front of us that's preventing us from actually fixing the thing that we broke. And very often we actually eject from the process so that we can do break-fix work against production, and sometimes those fixes don't make it back into our regular flow. And so we create this chaotic environment even though we were trying to create quite the opposite. And so what a lot of these companies that are effective at this have figured out is, well, it seems like no matter how hard we try to prevent mistakes, we keep making them. Maybe we should just stop trying. Maybe instead we should embrace failure. We know it's going to happen anyway. In fact, some companies are famous for making it happen intentionally just to see what they can learn from it, and maybe we can get to that point. But we have to start to think very, very differently. And instead of being in a situation where we want there to be a large distance between failures, mean time between failure, MTBF is a primary metric, to let's make failure cheap. Let's make recovery very, very fast. Let's make it so fast that it doesn't matter if we fail, how often we fail, how quickly these failures happen apart from one another, if we can recover so quickly that our users actually don't experience it. And so to do that, we need different tools and techniques, and we need to start thinking about this at the level of architecture, which is why I want to speak a little bit about this idea of resilient architectures, which in my mind, there's a lot that we could talk about that if there's three things that if we get right, we'll be on the right track. The first is enhancing observability. The second is simply leveraging well-described, well-known resiliency patterns. And the third is embracing chaos. So when we talk about enhancing observability, what does that mean? There's a lot of conversation about this in the industry right now. I like to simplify it down to we need the ability to see. If you think about almost any endeavor, the ability to see what effects the actions that you take have is incredibly important, because if you can't see, you don't know if your actions are helping you or hurting you. Drivers need to be able to see. Pilots need to be able to see. If they can't see physically, they fly with instrumentation to help them see. We can't actually see what our software is doing, but we can add instrumentation to the software to help us see what it's doing. Who's read the Site Reliability Engineering book from Google? A couple of folks. If you haven't read this, you don't have to read the whole thing. There's a lot in here that is very specific to how Google runs Google. And if you're not Google, there's going to be a limit to the utility that you'll get out of it. But at the very beginning of the book, chapters 3, 4, and 5 really outline a set of principles that I think are incredibly helpful in any situation. If we learn these things, then it can really help us. And I want to zoom in on just one of those chapters and talk about service level objectives and management. Because ultimately, we have to define what resiliency means for us. I'll go into a company and I'll ask them, what is it, what are your resiliency requirements? And they'll tell me things like, the system must be highly available. I say, well, what does that mean? Well, it can't go down. I said, okay, we're done here because that's not possible. So we need to think a little bit differently. We're going to have 5 nines for every service that we have. I find that entertaining because if you think about the connection between the mobile device and your software, that's not a 5-9 connection. So even if you can achieve 5 nines, nobody's going to get the benefit of it anyway, and every single 9 that you add to that availability is, in many cases, an order of magnitude more expensive than the last 9 that you added. And so you're burning a lot of cash for very little return. So I instead like to think about specific measurements. What is it that we want to measure? And this was what Google calls SLIs, service level indicators, quantitative measure of some aspect of the level of service that we're providing, like request latency against a particular service at a particular time. And so we need to clearly identify what are these things that we care about. But that's not enough. We also need to think about what is an acceptable measurement for this SLI, what's an unacceptable measurement. Probably even more important than that, what's normal and what's abnormal. You say, oh, CPU has spiked to 97%. Is that good or is that bad? I don't know. I have no idea. Are the users happy? Yes, the users are happy right now. Well, maybe that's okay. So we have to understand for the system that we've created and the type of load that we're putting on it, what is normal, what is abnormal, what is acceptable, what is unacceptable. We call these service level objectives. And so we need to clearly identify what the service level objectives are for this particular piece of software. And if we do that, then we can start to think about how do we architect a system to meet these particular objectives. Now, if we go one step beyond this, we go to the thing that a lot of us talk about informally, which is this notion of SLAs, or service level agreements. A lot of us talk about SLAs, almost none of us are actually doing SLAs, because SLAs are like contracts. They specify behavior, but then they also specify consequences for failing to behave in that way. So for example, if my uptime does not fall within a given range, then you don't have to pay me as much money. If that's not what we're talking about, we're not actually talking about an SLA. And so to even have an SLA, you need to have good SLIs and good SLOs. But if you have good SLIs and good SLOs, you don't really need to go to SLAs unless you're using that as a selling point for the software. Once we have these, we need to think about how we're going to measure them. And the primary thing I want to stress is a focus on distributions. Lots of tools make it very easy for you to get averages. Averages are indicative of almost nothing that you care about, because very little of what we actually do in this business has a normal distribution wrapped around it. If you look at this graph, which I pulled straight out of the book, we're measuring latency. Typical request served in about 50 milliseconds. But as it turns out, 5% of those requests are as much as 20 times slower. We follow the graph out to the right, doesn't look like it's changing that much. If we go up into the 95th percentile, we see this really spiky distribution of latency. We say, okay, well that's just 5% of the requests. So that's rare. 95% of my users are having a good experience. Are they? Let's look at it from a different perspective. So this is a table I pulled out of a great blog post you ought to read called Everything You Know About Latency is Wrong. And in this blog post, the author talks about many things, but catalogs this table that a speaker presented at another conference, lists a bunch of popular websites, and when you visit one of those pages, how many requests are actually generated for that page view. Then goes on to calculate the probability of one of those requests experiencing a 99% latency. And what you see is for every website except for Google.com, there is a greater than 50% chance of that visit experiencing a 99% latency, which means that that is what your users are actually encountering on a fairly regular basis. Now, if that 99% latency is the favorite icon, who cares? If it's on the critical path for actually building that screen, then that can be a very bad experience for those users. Now, if you're wondering what is it that you should actually measure, Google helpfully identifies 4 golden signals. Here's a good place to start. So we can begin with, obviously, latency. We've been talking about that quite a bit. Also measuring traffic, how much demand we're placing on the system. Errors, what is the rate of requests that actually fail? And then finally, saturation. This is how full your service is. There's something that is constrained in your system, whether it's memory constraints, I/O constraints, CPU constraints. There is a tipping point beyond, if you pass that point, your service is going to no longer actually be able to do its job. And so we need to measure and understand, well, what is the thing that constrains our application's performance? And then what is that tipping point? So that we can watch as we approach that tipping point and ensure that we don't cross over it without adding additional performance or starting to throttle requests or however it is that we've determined to manage that. Now we look at things like services, microservices, web service, I don't care what kind of service we're talking about, there's a certain amount of telemetry that we're interested in. We want to know about things like traceability, which is the metadata that describes what is this code that we have in front of us that we're trying to ascertain the performance of. What is the get SHA? What are the package coordinates in the Maven repository? What are the API versions that are published? If we're using feature toggles, what features are toggled on or off? Just what is the contextual information that we need to know in order to troubleshoot? We need to measure things like health. You know, what determines that your service that you're operating is healthy or unhealthy? Is it a process is running? Is it that it's listening on a port? Is it something more complicated than that? We need to understand what that is and provide a way to view that. We've talked a lot about quantitative measurements. There's also qualitative observations. There are things that we care about but that we can't measure with numbers. And so this is the realm of proper logging and exception reporting, things like that. But if you think about a graph of services, even if you know all of this information for every service in the graph, you still don't know enough to tell you about the health of the system as a whole. And so there's also integration telemetry that we're interested in. If we're using techniques like circuit breakers that I'll talk about a little bit later, those circuit breakers are proxying requests from A to B. And so they know a lot. They know the request rate. They know the response latencies. They know the error rate. They know the request rejection rate. And so they can measure all of that information and report it back to us. If we're trying to understand the lineage of a request, what are all the services that have to participate to carry a request from a user to a successful response? We have distributed tracing as a way to help us gain that information. If we're doing message-driven architectures, our message middleware can give us some of these metrics. And then going back to logging, you know, if your degree of sophistication of analyzing logs is download the log files from all the different servers and then somehow try to grep your way through them, you're feeling a lot of pain in these troubleshooting situations. But if we can start to attach request correlation IDs to logging messages, we can start to automatically stitch those logs together into a story that we can read and understand the behavior of that system. Now, I come from Pivotal, and that's where Spring lives. And part of the emphasis in Spring Boot since we started building it was to provide this type of telemetry as much as we can. So if I simply add the Spring Boot actuator to my application, I can start to get nice endpoints like /health that tell me about the various components within my application and how healthy they are. If I want to get that metadata What is my Git SHA? What are my Maven package coordinates? I can actually have those accessible very easily through the /info endpoint on Spring Boot. I start to look at things like integration telemetry. Leveraging Spring Cloud Sleuth combined with Zipkin can help me to create those lineage graphs to understand what are all the components participating in fulfilling this request and what is their contribution to the latency of that particular request. So lots of examples out there. Of course, these links will all be published in the slides. You can get to all this from my website as well. So now we have the ability to see. The next thing that we want to do is start to leverage resiliency patterns. And the cool thing about resiliency patterns is they're fairly simple, and we've been using them for a long time, just not really in mainstream development. And so there's really good documentation out there that helps us to learn and leverage these things well. And then again, as we've gone down this road into microservices and more distributed systems, our frameworks are starting to make it easier and easier for us to apply these. So where do we start? Let's start at the simplest possible thing we can do. Start to embrace the usage of timeouts. Now I know that you've come to a conference like this, you're a very intelligent person, and you never do anything that could block a thread without applying a timeout, right? We're all perfect in that way. Obviously we're not, otherwise I wouldn't be talking about this. But it seems like such a very simple concept, and yet we very often don't leverage it. And one of the reasons that we don't leverage it is that we don't think about it. We assume that as we've used all these really nice frameworks, that these really nice frameworks are out there to take care of us. And they're going to happily provide us with sensible defaults for all of the things that we need. As it turns out, that's actually not the case. And so you think about what could block a resource like a thread, and when you run that operation, how are you going to ensure that it's going to complete at some point in time? Successful completion, error completion, I don't care. I want it to stop and give me back control. And so I need to think about injecting that control into my code. If you're looking at some libraries, and you've got 2 method calls to choose from, and one of those method calls takes an optional timeout argument, always choose that one, because the other one almost certainly will happily wait forever. Now, Spring really wants to take care of you, but guess what? If you use REST template, it still doesn't have a default timeout value. See, Spring trusts the HTTP components library to take care of you. As it turns out, HTTP components trust the JDK to take care of you. And the JDK just says, I'm happy to wait forever. And so if you don't actually set a timeout value when you construct your REST template will happily wait forever. Now, if you've wrapped other resiliency patterns around REST templates, sometimes that saves you. But I always like to think about the types of requests that I'm going to create and put some fail-safe mechanism in place so that if everything else breaks down, at least REST template's going to return me control. Next, retries. Sometimes requests fail, clearly. Sometimes we repeat the same request right away, it succeeds. Why? We don't know. It could be that that system was under heavy load. It could be that that system was unhealthy, and at the very next instant it becomes healthy again. It could be that there's something wrong with the network connection that was a temporary hiccup. We have no idea. And so when we're in a situation where we have those types of intermittent failures, sometimes it's very good to build in some retry logic. So we have these potentially transient failures. The simplest thing that we can do is right away, as soon as we experience one of those failures, try it again. Now, if we take this too far and we're constantly retrying immediately, what we could do is be taking a service that's unhealthy on the other end of that call and abusing it to the point that it can never become healthy again. So it's very often a good choice to build in some sort of a back off. Maybe we want to wait a second, and then 2 seconds, and then 3 seconds. Maybe we want to get fancy and have a random back off or an exponential back off built into that. But either way, each successive request, we wait a little bit more time before trying again, and then certainly at some point we want to probably give up. If we have retried 3 times or 5 times, whatever metric we pick that makes sense, if it does not recover within that period of time, let's give up and move on. And then more importantly, again, think about the observability aspects of this. Log all of these retry operations, log all of the serving of those requests on the other side, build in that correlation so that you can analyze those retries. It could be that you can catch some emergent property of the system that if you simply tune both sides of that interaction a little bit differently, all of these retries go away. But without being able to read and understand that story, you'll never be able to do that. Now, we have a lesser-known library in the Spring ecosystem called Spring Retry that helps you to do this in a very declarative way. So I have a method here that tries to acquire things, and it will return a response entity of strings. Very simple method, and I have annotated it as retryable. What that gives me is a very basic retry strategy that retries effectively immediately up to 3 times. And at 3 times, it will delegate to another method annotated with recover. And so in this case, I have implemented really a very basic circuit breaker-like pattern that will retry a few times and then fail over to another method that does not bubble that error back up to the client, but just returns some default response. Now, if I want to add back-off behavior to that, I can send parameters into my retryable annotation. Here I've increased the maximum number of attempts to 5, and I have set back off to a back off annotation with various parameters that will start with a 100 millisecond delay and then multiply it up to 1,000 millisecond delay and then introduce some random behavior to that as well. Now, if I want to take that back off strategy and I want to turn it into an exponential back-off strategy, that's as simple as declaring a bean of type back-off policy and returning an exponential back-off policy, and now all of my retry logic within that particular Spring context is going to have that back-off applied. Bulkheads. We take ships and we divide them up into multiple watertight compartments. Why do we do that? So that if we get a hole in the side of the ship, we can seal that compartment and limit the scope of the flooding so that the ship doesn't sink. If we didn't have those bulkheads, you get a hole in the side of the ship. It's very hard to keep that ship afloat. The general principle is we can divide systems such that failure modes don't have to bring the entire system down. This is one of the first reasons that we started to employ microservices. We find a failure mode. We say this failure mode should not affect these other things. Let's segregate them into independently deployable services so that this failure can't affect this thing over here. But we can zoom into an individual application. We're still using threads, and I think most of us still are. We're not all reactive just yet. A lot of things are still using thread pools. We can segregate operations into independent thread pools so that one unhealthy operation can't necessarily take down all of the available threads in a JVM. If we think about zooming out to the level of a data center, we have the same ideas. We have availability zones. These are independent data centers. And what they allow us to do is to spread our application across those failure modes so that if a data center goes down, our application is still running in this other data center. And so if we look at all the different levels of our infrastructure, of our architecture, our different applications, we can think about different places that we can divide our application and segregate our applications so that failures in one area doesn't affect the other through the application of all these different types of bulkheads. And then finally, the one that everybody loves to talk about is the circuit breaker. which is bringing the circuit breaker in an electrical system metaphorically into my logic, which is basically, in most cases, a three-state state machine. I'm sure a lot of you have seen this particular diagram before, but we have a closed state, an open state, and a half-open state. And while we're in that closed state, we're allowing requests to flow through to our downstream dependency. We get enough failures in that state in a certain period of time, we trip the breaker and we stop talking to the downstream service because we basically have decided at this point that's futile. This is very often, again, where we return some fallback or default response. But then periodically we transition into this fun state at the bottom called half open, which is basically the same thing as closed, except it only processes one request before it retransitions. And if that request is successful, we reset the breaker to closed. If that request is a failure, we retrip the breaker to open. Layering behavior like this into a Spring Boot application or Spring Cloud application can be as simple as adding a hystrix command annotation to a method and then pointing at another method which will provide that fallback behavior. So again, Spring Retry, hystrix, through Spring Cloud Netflix if you're doing Spring, and you can get some good properties there. Which leads us to point number 3, embracing chaos, which in many ways is the dark counterpart to site reliability engineering. If SRE is providing all of the light, chaos is providing all of the darkness, and we have to have those things in balance to see if they're actually doing their jobs. The question that I want to ask you is, how do you know if your system will tolerate failure if it hasn't failed yet? You've built all this observability into the system. You've layered all these resiliency patterns in, and your system hasn't failed yet. Is your system resilient? Is it highly available? Is it any of those things? The only correct answer to that is, I don't know yet. So you have two options to learn if your system's resilient or not. You can learn when it actually fails for the first time in production, and you can't predict when that's going to happen, and it will probably happen at a bad time for you. Or you can control that and inject that failure at a specific point in time when you are prepared to learn from it and then actually gain that learning when it's a little bit cheaper to do so. And this is what we call game day exercises. Very simple. We pick a point in time, we simulate a catastrophic event, and we practice our response and evaluate and learn from our ability to respond, both at the person level and at the system level. The point being, you don't want to evaluate your emergency readiness in an actual emergency. Now, if you're a sports fan, you know that whatever sport you pick, the teams don't learn how to play the game during the championship. They practice, and they practice, and they practice so that when they show up, they already know what their capabilities are, and they already know what they're going to do. But let's dial that up a notch. Some of the coolest things that happened in software engineering happened in the 1970s. Some of the best papers that were ever written about how to do our jobs were written in the 1970s. Most of them before I was born, most of them before a bunch of us were. And Yao and Chung wrote this great paper called The Design of Self-Checking Software. And their idea was, we're going to take the air traffic control system and we're going to insert fake ghost planes into the air traffic control system. And their theory was, their hypothesis was that if all the ghost planes land safely and all the real planes land safely, then we can actually trust the air traffic control system and the human operators. Now, they never actually implemented this. I have no idea if that's a good thing or a bad thing, but they didn't do it. But these ideas kind of rested under the surface for several years. And a few years ago, we start hearing about things like the chaos monkey. If you're not familiar with the chaos monkey, basically it is a process whose job is to wreak havoc in the production system. it will randomly terminate servers at will. And as a developer, as an operator, your job is to write software that is resilient to the chaos monkey. The net effect of that is that server failures become a non-event if you live in this environment. Or, you don't get to write a whole lot more software. Now, in our world at Pivotal, we do a lot of things with Cloud Foundry, and in Cloud Foundry, we have written our own army. It's not the Simian army, it's the Streptocerini army, but we have the Chaos Lemur and the Chaos Loris. And so I want to quickly show you a little demo of a service that I'm putting a lot of load on, and I'm generating a bunch of log messages from, and this is from one microservice to another. And what I'm going to do is talk to this Chaos API and tell it about this application. And so now it knows about this application up there on the right that's receiving all that load. I'm then going to set a chaos schedule, which is going to run every 15 seconds. That's probably too much, but it works great for a demo. And then I'm going to link the schedule together with a chaos probability, which is basically saying that every 10 seconds, every 15 seconds, we have a 10% probability that this server is going to be terminated. So I now start watching the logs for the Chaos Loris, and we see these chaos events happening every 15 seconds. And those are going to scroll by periodically. We'll speed up time a little bit to make things go a little bit faster because we're running low on time as it is. And eventually, I believe the 5th instance of this chaos schedule, we're actually going to get a server termination event. Now, on the left-hand side over here, we're watching the circuit breaker between the two of those. So with this application termination, and there's our Linux container being destroyed, we should see this circuit breaker start to notice that that connection is now unhealthy. And so it goes to red. We now have an open circuit, and we're returning default responses. Notice we're still getting 200s for all these client requests, even though this thing is down. Now, Cloud Foundry, being the nice, fun platform that it is, starts trying to reset the Spring Boot application. Funny enough, the Chaos Lemur strikes again while the application's trying to start back up. But eventually, we get back to normalcy. What I really like about that, though, is that while I'm trying to restore health, the Chaos Lemur strikes again. That feels a little bit more like real life. Very often, it's when you're trying to fix things that other things start to break. And so if we have that kind of an environment where that happens and it's not so controlled, it's much more chaotic, then that helps us to really evaluate our ability to respond. And so going from this basic introduction of chaos monkeys and chaos lemurs, we can get to a more sophisticated practice that has come to be called chaos engineering. And this, if you go to principlesofchaos.org, is the discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. So a few basic principles here. The first is build a hypothesis around steady-state behavior. Think of a thing that you can measure that is a good proxy for customer success. And when you have that thing, try to understand, is this a very predictable metric for user behavior? Netflix started with stream starts per second, or SPS. And what they found is that people's viewing behavior throughout the course of a day and throughout the course of a week is very, very predictable in a given geography. It's so predictable that if there is a small deviation in observed viewing behavior, they know that Netflix is sick. And so have that measurement, and your hypothesis is that, well, it's steady state. So as I start to inject chaos into the system, that should not affect behavior. Then you start to inject that chaos by varying real-world events. What are all the things that can and will go wrong in the real world? And start to simulate or actually inject those types of failures into your systems. Do that through experiments. We plan these things out, we code up the behavior, we divide into a control group that doesn't experience chaos and an experimental group that does experience a particular type of chaos, and we compare the two. And then we automate these experiments so that they're continually running. We don't have to have humans involved. We know that every day as we go to work, these experiments are going to be running, and even as we build more resiliency in the system, we're continually running these tests. Just like you run your unit tests every time you change code, even the unit tests that theoretically you shouldn't have affected, because guess what? You don't always know whether you've affected those parts of the code or not. We're now doing the same thing at the level of the production architecture. And then last but not least, because we're running these experiments in production, and why do we do that? Because we can't exactly duplicate the production environment, nor can we exactly duplicate the behavior of the real production users. But because we're doing that, sometimes we're going to affect customers through these experiments. And so what we want to do is our level best to ensure that as we affect customer experience, that we do so minimally. And this is what we call minimizing the blast radius. So, review time. Step 1, stop trying to prevent mistakes. Embrace failure. Step 2, focus on mean time to recovery. Focus on making failure cheap, making recovery fast, so that as all of these failures happen, you're not affecting customer experience. Third, enhance observability. None of this stuff works if you don't have the ability to see what's going on in the architecture. And so leverage instrumentation, monitoring, identifying service level indicators, service level objectives, so that you can understand. Take the well-known, well-described, well-documented, even frameworked resiliency patterns and build them into your software. All the places that you know for a fact your software has weaknesses, shore up those weaknesses. And then once you've handled all of the things that you know can go wrong, leverage and embrace chaos to help you with the things that you don't know you don't know. And then as you continue to learn, continue to repeat this process, and you will build increasingly more resilient architectures that will be able to handle all of these stressors. So maybe time for 1 or 2 questions?
Yeah, we have one question here. So if the people know it's an exercise, is the simulation giving meaningful results? So can you really then rely on the responses that they have if they know it's planned?
Can you repeat it one more time? I couldn't hear.
So if the people know it's an exercise, if so, is the simulation giving meaningful results?
Okay, so very good question. If I know it's an exercise, when you have the fire drill, right? Nobody actually takes that seriously. We all walk out of the building and we make jokes, and we eventually go to this place we're supposed to go, and we get irritated because we want to get back to what we're doing. We go back and we don't take the practice seriously. So how does that not translate into our behavior in this type of a scenario? One of the interesting things that, say, Amazon did in the early days was they would tell their teams, an exercise is going to happen this week. I won't tell you specifically what day it's going to happen, but I will tell you that you're going to have to stay at your desk until we've actually resolved the problem, and it's going to be in the real production environment. And so there's a certain level of tension of knowing something's going to fail this week. I don't know precisely what it is, and I don't know precisely when it's going to happen, so that I am on a state of kind of serious alert. Now, as you move into the chaos engineering aspects of this, there's a lot more randomness built into it. And so you really don't know when it's going to happen. So if you inject just enough randomness into the process, then it's not going to be quite as predictable of an experience where you don't take it seriously and you don't behave as you really would in a real emergency, because it is much more approximate to a real emergency.
Yeah, we don't have time
No
for
time?
more.
Okay.
Yeah.
Thank you very much.